Okay, so line integrals. Here's what we know how to do so far from Calc 1 and Calc 2. We took a single integral, in which case we integrated over an interval. Last chapter, we looked at double integrals, in which case we integrated over an area in 2 space. We also looked at triple integrals, in which case we integrated over a solid in 3 space. So that's what we've done so far. Now what we are going to do is we will be integrating along a curve. Okay, and of course the natural question, besides how do we do that, is why would we bother? So here are some motivations for us why you would choose to integrate along a curve. It's related to mass, fluid flow, force, and as you see on the board from one of the objectives, it's also related to work. So we're going to jump right in with line integrals. You are going to have some curve. We're going to call this curve C. You're going to have some point P naught, and then the end point we call P of n. And what you do is you split this curve along equal intervals. So we're going to be taking points all along your curve. One point is P of I minus 1. The next point is P of I. So you have that interval then. What you're going to do, like we've done before, is you're going to choose some point in that interval. I'm going to call it P of I star, and it's X of I star, Y of I star. Oh, that's cool. There we go. Okay, so that curve C, we're going to define parametrically. So X is going to be some function of t, Y is going to be some function of t, and we're going to say that t is from A to B. So then if we want to calculate the line integral, we're going to be summing up from I equals 1 to n. You're going to take f of those points, and you're going to multiply by delta s of I. This represents the length of the subarc. So what this is saying, you have all these intervals. Choose some point in each interval, plug it into the function, multiply by the length of that arc. That's what you're going to be doing. So this leads us to the definition of a line integral. If f is defined on a smooth curve C, so that's important, it has to be smooth. And again, C is going to be defined parametrically. Then the line integral of f along C is the following. Okay, so you're going to have a single integral with a C there. It'll be f of xy ds. And then this is the limit as n approaches infinity of that sum that we wrote above. Okay, there are two things that are very important here to notice. The first one is that little c is not a bound. That tells us that this is a line integral. So that tells us that we are integrating along the curve c. S also tells us that this is a line integral. So those two are the notation that tell us we're doing a line integral. Okay. One thing to recall is formula for arc length. It's the integral from a to b, the square root, derivative of x with respect to t, derivative of y with respect to t, dt. So here's where that leads us. Line integral. Way to calculate that, it's going to be the integral from a to b of f of x of t, comma y of t, and then the arc length formula. Bless you. Okay, I have to fix something. I'm very sorry. This s is a little s, not a big S. We are going to get to big S eventually, so that's very important. Little s line integral. This you will also see written sometimes as the magnitude of r of t. Brian?
The delta SI, is that still uppercase S?
No, lowercase. Okay. So here's why that makes sense. If you recall, do you guys remember doing arc length parameterizations? Do you remember that term? Okay. If you remember, when you took the derivative of an arc length parameterization, you got dx dt squared, add dy dt squared. So what that leads us to then is that ds, which is here, is that square root dt. Okay. So here's our first example. We are going to evaluate the line integral of 2 add x squared y ds, where c is the upper half of the unit circle. Okay, so first thing we want to do is draw a picture so that we know what C is. In order to calculate the arc length, so this here, we're going to need to have x and y defined parametrically. This is the unit circle, so in this case x will be cosine of t, y is going to be sine of t. Okay, so what this becomes, this is now a regular interval, or integral. T is going from 0 to pi. Instead of x squared and y, we need the parametric representations. So we're going to have 2 add cosine squared of t sine of t. And then we need dx dt, so negative sine, but then we're squaring it. So sine squared t. Derivative here is cosine of t, but then we're squaring it. And then dt. So that's 1, so we just get the integral from 0 to pi of 2, add cosine squared t, sine of t, dt. And then that's just integrating like normal. So this will give us 2t, subtract 1/3 cosine cubed t from 0 to pi. Final answer being 2 pi, add 2/3. Okay, any questions so far? Okay, we're gonna look at another one then. We are going to evaluate line integral of x ds, where c is the following. Okay, so the first thing I want us to notice is we are integrating along two different curves here. So we're going to need two different line integrals. This first one, the y equals x, I'm going to call that curve 1. The y equals x squared, I'm going to call it curve 2. So we're going to have to do two different line integrals. Let's start with C1. So C1 is the line y equals x. We need a parametric representation for this. If we call x t, that means that y is also t, and t is between 0 and 1. If you plug in 0, you get the point 0, 0. If you plug in 1, you get the point 1, 1. So this then will be the integral from 0 to 1. Bless you. X is t. We have the square root of dx dt squared plus dy dt squared dt. So this is 0 to 1 of t root 2 dt. Which is root 2 over 2. So that's the first one. Now we have to look along C2. So that is our y equals x squared. If we try the same method of parametrizing as we did before, and we choose x to be t and y to be equal to t squared, is that going to work? If you plug in 0, what do you get? 0, 0. If you plug in 1, what do you get? 1, 1. What's the problem? If we go from 0 to 1, doesn't that start here and go the opposite direction that we want? Okay, this is not going to work. Instead, x is going to be 1 minus t. Y then will be 1 minus t squared. If I plug in 0 now, I get 1, 1. If I plug in 1, I get 0, 0. So this now has the same orientation as the curve above. So this then will be the integral from 0 to 1 of x, so 1 minus t, times the square root dx dt squared, so negative 1 squared, plus 2 times 1 minus t times negative 1, all of that squared. Simplifying that square root, we get 1 minus t, the square root of 1 plus 4 times 1 minus t squared. In this case, you're going to do a u substitution. If you consider your u to be 1 plus 4 times 1 minus t squared, your du then would be 4 times negative 1 times 1 minus t. Are you okay if I don't actually substitute the u in, if I just integrate? Yeah? Okay. Oh, I think I missed a 2 here from this 2. So here we should have had a negative 8, but we didn't. That gives us a negative 1/8. This will be to the power 3 over 2, which gives us a 2/3. And we have 1 plus 4 times 1 minus t squared to the power 3 over 2 from 0 to 1. Which ends up simplifying to 1/12, 5 to the power 3 over 2 minus 1. Final answer then is when you add those two together. So we have root 2 over 2, add, bless you, 1/12, 5 to the power 3 over 2 minus 1. Any questions before we go on to talk about what this actually means? Yes?
How do you get the 1 minus t equals s? Like at the start, C.
If you start t at 0, if I do 1 minus t, it'll start us at the beginning. So it's going to involve a little bit of guessing and checking.
Okay.
I know that's not like the best answer,
Yeah.
but a little guessing and checking. Okay, here's an important note for us to know. Right now, we have arc length parameterizations. What that means is the ds. So S is an arc length parameterization. So orientation does not matter. So eventually we are going to do line integrals that are not ds, they're dx and dy, in which case the orientation does matter. What I mean by orientation is this direction right here. So you know how I said right here, this wasn't the right parameterization to use because it went the wrong direction? That direction doesn't matter in this case because it's ds. So if we do C2 again, and we use that initial parameterization that we came up with, but then it said it wasn't very good, we should get the same answer. So in this case, we have the integral from 0 to 1 of x times the square root dx dt squared dy dt squared, which ends up being 4t squared plus 1. If we integrate, we get 1/8, we get 2/3, we get 4t squared plus 1 to the power 3 over 2, being evaluated from 0 to 1. Which, if you trust me, it ends up being 1/12, 5 to the power 3 over 2 minus 1. So it ends up being exactly the same as what we got before. I cannot stress enough to you that this is only because it's ds. So ds, the arc length parameterization. So as soon as we enter notes in like 10 minutes where it's no longer ds, the orientation matters. Alex?
So for ds, do we still have to do it like the right way, where we're going from the start to the end?
Technically, no. Okay. Questions on evaluating line integrals. Okay. So besides evaluating them, we need to know what they mean. So that's what we're going to talk about next before we go on. Two main interpretations that we're going to talk about. The first one, let's say that your function f, so f of x, y, z, represents density. So if your function represents density, then the line integral rather, over the curve C of f of xyz ds is the mass of a thin wire that is shaped like C. Let's say that f of xy is a solid or a curve. Then we can calculate the area underneath the curve. By taking the line integral over the curve C of f of xy ds. So here's what I mean by that. Let's say that f of xy represents a plane, maybe. If we have some curve C that's in the xy plane, and we map that curve up onto the solid, this line integral is going to calculate this area. One other thing for you to know, related to question 1, we are still finding centers of mass. It's going to be almost exactly the same as what you did before. If you are finding x bar, it's 1 over the mass, the line integral this time of x times the density ds. Okay. Are we ready to keep going? Okay, so far, here's what we've done. We've talked about a line integral with respect to arc length. And that looked like this. What I told you we were going to introduce is a line integral, this time with respect to x and y. So they're going to look very similar, so you're going to have to pay attention. You're still going to have that c. You'll have f of xy. Instead of ds, though, you could have dx. You could have dy. So the c tells you that it's a line integral. So anytime you see the c, you know it's a line integral. If you are doing a line integral with respect to x, like the first one, this will be the integral from a to b of f of x of t, y of t. This should be pretty intuitive. Dx is x prime of t dt. Y is very similar. It's going to be f of x of t, y of t times y prime of t dt. Okay, this is a case where orientation matters. Dx, dy, you need to parameterize the curve correctly. Even more fun than that, oftentimes these will occur together. So it's very common to see something like the following. Line integral over the curve C of p of xy dx, add q of xy dy. In which case you're going to do exactly what it says above. You're just going to have to do both of them. Okay. Let's look at an example of what that would look like. We are going to evaluate line integral of y squared dx, add x dy, where c is as shown. We're going to do two of them. We're going to do part A, which is one curve, and part B, which is another curve. Okay, so we're going to have this point -5, -3. And we're going to have this point 0, 2. Curve 1 goes from -5, -3 to 0, 2 in just a line segment. Curve 2 is also going to go from -5, -3 to 0, 2, but this time it's parabolic, or a curve rather, the equation of which is x equals 4 minus y squared. So part A, we are going to look at curve 1, which is a line segment. First thing we need to do is we need to parameterize that line segment. That should be something that is not surprising, right? Do you guys remember how to parameterize a line segment? Not at all. What? We don't know how to come up with an equation of that line segment? Oh my god. That's very concerning. Here's the formula. R0 is where you're starting, in which case -5, -3. R1 is where you're ending, so 0, 2. So R of t is 1 minus t times the vector -5, -3 plus t times the vector 0, 2. R of t then, we're going to end up with multiplying all that in, multiplying all that in, simplifying. If you trust me, it ends up being -5, add 5t, and 5t minus 3. So here's what we get from that. X of t is equal to -5 plus 5t. Y of t is equal to 5t minus 3. Dx is 5 dt. Dy is also 5 dt. So now we have to do the calculating. We're going back to this line integral. So we are integrating from t equals 0 to t equals 1. We have y squared dx. So y squared, 5t minus 3, dx is 5 dt. And then we have x dy, so x is that -5 plus 5t, dy is 5 dt. In your book, they put the dt's here and here. If you want to put the dt on the outside because it applies to everything, that's fine also. Okay. What this becomes, you can take a 5 out. Once you square, multiply by 5, combine all the like terms, you get 25t squared, subtract 25t plus 4 dt. Once you integrate and evaluate, you get negative 5/6. Okay, that was just part A. You guys with me still? Yeah? Okay. Take note, because this is dx dy, like I said, orientation matters, we also yet don't have a meaning for this. So ds, we wrote the meaning. It can be area underneath the curve. It can be the mass of a thin wire. We don't have a meaning for this. So don't think that it means much right now.
I have a question.
Yes?
Is t always in between 0 and 1?
Not always, no.
Okay, then where do we get the formula where it's like r of t equals 1 minus?
That's the formula for a line segment, so that is always between 0 and 1, yes.
Oh, is that like a formula for that's
Yes.
generalized to everything? Or all
For
these-
line segments.
Okay, line.
For line segments, yes. When we did line segments, I didn't use that formula a whole heck of a lot, but it's there. Okay. Part B. We now need to go along the curve C2, which was that x equals 4 minus y squared. Okay. So what is a nice parameterization, if we call y t, our x then can be 4 minus t squared. We have to figure out the bounds for t though. Well, t is based on y. Based on our figure, y goes from negative 3 to 2. So t then will be from negative 3 to 2. dy is equal to dt, and dx is negative 2t dt. Thank you. Okay, so now we can plug all this into our line integral. We will be integrating from t equals negative 3 to t equals 2. Bless you. So we have y squared, bless you. So t squared. And then dx. So negative 2t dt. Plus x. So 4 minus t squared. dy, which is dt. If you combine all the like terms, this is the integral from negative 3 to 2 of negative 2t cubed minus t squared plus 4 dt. Are you okay if I just tell you what it ends up being after you integrate? Yeah. Ends up being 245 over 6. Okay. This gave us a very important lesson. What I wanted to show us, if you noticed, both curves have the same beginning point and the same end point. The path matters. So two different paths with the same beginning point and same end point, the line integrals can be different. So path is very important. Okay, those are line integrals in 2 space. Line integrals in 3 space work exactly the same way. Do you want to? We probably should look at one, right? Probably. Okay. We have 2 more examples I want to get through. Max?
How did you get y equals t for part B?
Because y in this case is the independent variable, that's why I chose y to be t.
Oh,
Does that make sense?
yeah.
Okay. Okay. Next one is real quick, and then we'll do one more. We are going to evaluate line integral over the curve C of y sine of z ds, where x is equal to cosine of t, y is equal to sine of t, and z equals t, and t goes from 0 to 2 pi. two reasons I want to do this problem. The first one is that it's in 3 space and not 2 space, and the second one is I want to see if we remember what this would look like if we were to graph it.
Oh, I can't remember the name.
A helix. Yeah, a helix. It's one of the curly ones. Okay, so this then will become the integral from 0 to 2 pi. Y is sine of t. We have sine of z then, which in this case is t. ds. What? Oh, okay. ds is where you do the square root of dx dt squared, dy dt squared, dz dt squared. So derivative of cosine of t will be negative sine of t. Derivative of sine of t will be cosine of t. Derivative of z with respect to t will be 1. You get all that. All of this will be root 2, so I'm going to take that out. What do we do with the sine squared of t? Trig identity, yes. Double angle. Yep, 1 minus cosine of 2t over 2. Okay, and then if you trust me, I'm going to tell you it ends up being root 2 pi. Okay. Bless you. We have one more to do. Do I have 3 or 4 more minutes of your attention to do the last one? Very good. Okay, last one. We are going to evaluate line integral along the curve C of y dx plus z dy plus x dz, where C consists of the line segment from 2, 0, 0 to 3, 4, 5. Then the vertical line segment from 3, 4, 5 to 3, 4, 0. Okay. Hopefully we can see we're going to have to do this in 2 parts because there's 2 different curves. So first curve is that first line segment from 2, 0, 0 to 3, 4, 5. Our R1 of t then, I'm going to use R1 and R2 because it's 2 line segments. It's going to be 1 minus t. Starting point is 2, 0, 0 plus t. Ending vector is 3, 4, 5. If you trust me with the simplifying, this ends up being 2 plus t, 4t, and 5t. So we now are going to integrate from t equals 0 to t equals 1. We have y, so that's 4t, times dx. So the derivative with respect to t is 1 dt. We have z dy, so z is 5t. dy is 4 dt. And then we have x dz, so x is 2 plus t. dz is 5 dt. Okay. Can I trust that we are fine integrating that? Okay. It ends up being 24.5. Okay, then we have to do curve 2. We have to parameterize this one also. So it's going to be 1 minus t, starting at the point 3, 4, 5, ending at the point 3, 4, 0. This shouldn't come as a surprise. It's 3, 4, 5 minus 5t. So integrating from 0 to 1, we have y dx, so 4 times 0, plus z dy, plus x dz, oh, sorry, this is a -5. This one's really nice. It ends up being the integral from 0 to 1 of -15 dt, which is just -15. So final answer, add them together. We get 24.5, add -15, which is 9.5. Okay, do we have any line integral questions?